In this video, we will finish off the last two trends on the periodic table of ionization energy and electronegativity. So the term ionization energy refers to an amount, okay, so quantitative amount of energy that is needed to remove an electron from an atom. We are aware that electrons can come and go. So some metals tend to lose electrons, non-metals tend to gain. This energy value, though, is only to remove, okay, not gain an electron. This is very important that you understand. It is always about taking an electron away. And what we'll do is we'll go through the periodic table and we'll determine which atoms would need more or less energy to remove an electron. In order to understand the two trends in this video, you have to have a good understanding of the trend of atomic radius on the periodic table. And if you don't, you should stop this video, go back and rewatch the atomic radius video. Because the size of the atom is going to impact the amount of energy you need to remove an electron, as is the case for ionization energy. So the first ionization energy increases as you move across the periodic table. So if this is our periodic table here, crude drawing, as we move across a period, okay, where the number of energy levels are all the same, remember that your size decreases. And if the size decreases, and look right here at the lithium and beryllium example, if I want to remove one of those electrons away, it is more tightly held or attracted to the nucleus than it would be on lithium. Okay, it's not as attracted to the nucleus in lithium. So which one would be easier to remove? Well, this one would have a lower ionization energy. It'd be much easier to remove, so you don't need as much energy. This one here would have a higher ionization energy and require more energy to take that electron away. So some of my text is cut off here, but nuclear charge is going to increase while shielding is constant. Okay, again, because the number of energy levels is the same. Therefore, the attraction of the electron to the nucleus increases. And this is significant because if it is increasing, the electrons will be harder to remove. Okay, harder to remove. As we move down a group, how much energy do we need to remove an electron from an atom? Well, the first ionization energy is going to decrease as you move down a group. And why is that? Well, because the size of the atom increases because we're adding on all these extra energy levels, right? So we have all these extra energy levels that make the atom bigger. That outer electron is further away from the nucleus, so it's not held as tightly, or it's not as strongly attracted. And then as a result, the electron is further from that nucleus and will be easier to remove. The third trend we want to talk about is electronegativity. And this trend refers to the attraction for electrons in a chemical bond. And we credit Linus Pauling, he's a chemist, famous one, with this concept. And electronegativity is a very, very important concept. We're going to talk a bit more about it when we add on to chemical bonding in the next couple lessons. So when atoms bond, they can either transfer electrons in an ionic bond, or they can share electrons in a covalent bond. And electronegativity has more of an impact in covalent bonding because if the atoms are the same, then they're going to pull on those electrons equally. So remember, this electronegativity value is attraction for electrons in the bond. Well, if you have two hydrogens, they're going to have the same electronegativity value. And as a result, there's going to be an equal attraction for electrons. But when the atoms are different, the electrons will be pulled unevenly. One of the atoms might have a higher electronegativity or a higher attraction for electrons than the other. So the trend for electronegativity relates back to the atomic size of our elements. So electronegativity generally decreases as we move down a group. And as we move down a group, we know we have larger atoms. Larger atoms means that the nucleus, which is attracting those electrons in a bond, is far away. Okay, so that nucleus is so far away down a group that might have 6 or 7 energy levels surrounding it that it really cannot attract electrons and form a chemical bond. Electronegativity of our representative elements, so these are the group A elements which do not include transition metals. Okay, so not transition metals. We've mentioned already that they are often not part of the trends. The electronegativity increases as you move across a period because it is a smaller atom, and a smaller atom means that the nucleus is not far away, okay, or as far away anyways, relative to the metal side of the periodic table. Here are some values of electronegativities. My formatting of the slide is off. I don't know what happened, but what we can see is that fluorine's element is the most electronegative. And the reason for that is that fluorine is the smallest atom on the periodic table, except for the noble gases. Okay, so for hydrogen and helium, but noble gases don't bond. So this is why we don't include them in the trend for electronegativities. And in fact, if you look at the value of electronegativity on your periodic table, you'll notice there's nothing listed for the noble gases. This makes sense. They have full outer energy levels. They don't want to attract electrons in a bond. They don't need to. So you'll notice here that these non-metals, right, are sort of high up in terms of electronegativities. And then when we get down to, we just show you sodium here and cesium as examples, but those electronegativity values are quite a bit less, indicating they do not have a strong attraction for electrons. And the reason for that is because their atoms are much bigger in size. Nucleus is too far away. Here's a bit of a messy overview of the trends of the periodic table. And you'll notice that the arrows are either going to the right or going down. But in order to do that, either the trends are either increasing or decreasing. So you can stop the video, have a look at this for yourself. I know some of the font is overlapped, but this provides a good overview of our trends.